Hello there, and welcome to the Whispering Science, where we gently illuminate the wonders of the universe, one softly spoken fact at a time. Tonight, we'll be exploring the mysterious relationship between life, death, and the persistence, if any, of consciousness within the strange framework of quantum physics. Now, I do hope this isn't too interesting that it keeps you awake. But if it does, well, at least you'll have learned something fascinating about how the most fundamental science touches one of humanity's deepest questions. What happens to the mind when the machinery of the brain ceases its delicate dance? Before we begin, if you enjoy these slow science journeys, I'd be ever so grateful if you tapped the like button, subscribed, or even just left a comment telling me where in the world you're watching from and what time it is in your corner of the night. It's a gentle way to let me know that out there, across the swath of darkness, minds are quietly tuning into the same mysteries. So, settle in, get comfortable, and let's begin our quiet voyage into the paradox of consciousness. Imagine, for a moment, the calm silence that follows the day's activity. This stillness, contrasted with the vibrant hum of life, poses an ancient question. What is consciousness really? And does it vanish with our final breath? Or could it persist, somehow, when biology quiets? In science, paradoxes are invitations to wonder, and consciousness sits right at the heart of one of the greatest. On the one hand, the sum of decades of neuroscience suggests consciousness is inseparable from the brain's intricate plasma of electrical and chemical activity, a shimmering tapestry woven by neurons, synapses, and specialized brain regions. Yet, lurking beneath the comforting certainty of biology, quantum physics tells us that reality itself is far stranger than our everyday experience would suggest. In the quantum world, particles can exist in multiple states at once. Information seems to have indelible persistence, and the very act of observation changes what is observed. To some, the paradox of consciousness emerges here. Is our awareness simply a fleeting glitch of electrochemical activity, vanishing at the moment life ends? Or could quantum processes in the brain offer a potential, however tiny, however speculative, for consciousness to persist in forms not yet understood by biology? By pondering such questions in the gentle hours of the night, we walk in the footsteps of physicists and philosophers alike. The challenge is more than one of curiosity. It's an invitation to unravel the connections that bind our fleeting moments to the grand intricacies of the universe. As we explore further, you'll discover how the paradox of consciousness continues to intrigue the world's finest scientific minds, not as a puzzle to be solved in a single night, but as a mystery worthy of eternity's gentle, wondering gaze. As we gently proceed through this journey, let's focus now on defining life and death scientifically. In many ways, these two states are like the most fundamental turning points in nature's story. The difference between animation and stillness, between chemistry set in motion and chemistry at rest. But within science, to clearly communicate about such profound transitions, we need precise, operational definitions. Scientists generally regard life as a particular pattern of organization, a collection of dynamic processes rather than a single substance. Instead of a simple on-off switch, life is defined through the characteristics of living systems. Imagine a cell, the smallest unit of life, bustling with metabolic activity. Energy is taken in, waste is expelled, molecules are synthesized and broken down. This constant flow and renewal is guided by the information stored in DNA and managed by intricate networks of proteins. At higher levels, multiple cells organize into tissues, organs, and organisms, setting the stage for emergent phenomena such as movement, growth, response to stimuli, and, for a chosen few, consciousness. For all this complexity, though, biological life adheres to a certain list of criteria. These usually include organization, metabolism, homeostasis, growth, adaptation, response to the environment, and reproduction. A bacterium in the soil and a human being both qualify, though each expresses these features in unique and captivating ways. But what exactly is death, then? Death is perhaps best understood as the irreversible cessation of an organism's vital processes. In medical terms, for humans, this has evolved over time. Decades ago, the heart stopping was synonymous with death, but advances in resuscitation blurred that boundary. Today, scientists and physicians increasingly focus on brain death, a state where all brain activity, including the vital functions of the brainstem, has permanently ceased. The transition from life to death unfolds as a gradual, highly orchestrated breakdown, a process with its own specialized terminology. Apoptosis, for instance, is when cells deliberately self-destruct as part of development or in response to damage, ensuring the organism's overall health. Necrosis, by contrast, is uncontrolled cell death due to injury or illness. Systemically, as an organism approaches death, metabolic processes grind to a halt. Oxygen-starved cells falter, molecular pumps on membranes lose their charge, and the chemical gradients that sustain the spark of life begin to dissipate. The moment that separates life from death is, thus, not a single instant, but a process. Neural activity sputters out. The intricate electrochemical orchestra wanes until only silence remains. Scientifically, we can measure this with techniques like EEG, electroencephalography, which traces the faint thunder of a living brain and flatlines to stillness with the loss of all organized activity. What's particularly thought-provoking is that this scientific boundary, though increasingly precise, at its edges still holds some uncertainty. Cellular life can persist for minutes or even hours after clinical death, as tissues retain metabolic flickers. In remarkable cases, stories abound of people revived after extended periods of apparent death, prompting renewed attention to exactly where the dividing line lies. In the context of our broader question, whether consciousness might persist after these processes end, science's evolving definitions matter. They anchor us in observable phenomena and establish rigorous criteria for measuring when life is present and when it is finally, irretrievably gone. And so, as you settle further into the calm of this night, consider. Life, as science defines it, is ultimately a pattern, complex, dynamic, yet finely balanced. Death is the disruption and dispersal of that pattern. Yet, as we'll see, some scientists, especially those pondering the quantum world, wonder if death, at the deepest level, leaves a trace, an echo of that pattern, preserved in the subtle fabric of reality itself. As we continue our journey, lulled by the quiet rhythms of night, let us ease our attention toward the basics of quantum mechanics. This branch of physics is famous for its strangeness, but at its heart, it is the language nature uses at the smallest imaginable scales, describing the behavior of atoms, electrons, and the particles that compose all matter, including you. Quantum mechanics began at the dawn of the 20th century. Scientists like Max Planck in 1900 and Albert Einstein in 1905 first proposed that energy comes in tiny discrete units called quanta. These early discoveries soon blossomed into a radical new physics. Niels Bohr, Werner Heisenberg, Erwin Schrödinger, names whispered through science's corridors, helped develop theories explaining that on atomic scales, the universe isn't as straightforward as it appears in our everyday world. Let me guide you through some of these essential principles, as softly as the night breeze. First, the concept of superposition. This is the idea that particles do not exist in a single, definite state, but instead can be in many states simultaneously, up until we measure or observe them. Schrödinger famously illustrated this with his cat in a box, a hypothetical animal both alive and dead, until we open the lid and look. While the physics does not directly apply to large animals in boxes, superposition plays out constantly among the particles inside you and around you. Next is entanglement, an almost magical seeming connection between particles. Once entangled, the state of one particle instantaneously affects the state of another, no matter the distance between them. This was so peculiar that Einstein famously referred to it as spooky action at a distance. Yet, experiments have repeatedly confirmed that quantum entanglement is real, a fundamental property of our universe. Then, consider uncertainty. Heisenberg's uncertainty principle, articulated in 1927, tells us that we cannot know both the exact position and exact speed of a particle at once. The more precisely we know one, the fuzzier the other becomes. This isn't due to flaws in our measuring devices, but a consequence of reality itself, when you look closely enough. Even the very act of measuring a quantum system changes it, a fact central to the so-called measurement problem, which we'll return to later. At the heart of all this is the quantum state, which is represented mathematically as a wave function, a kind of probability cloud describing all possible outcomes. When not observed, a system evolves through a range of potentialities, but sharpens into a single outcome upon measurement. This dance of possibility and actuality underlies everything from chemical reactions to the light that glimmers on your curtain and the very signals flowing through your nerves as you drift towards sleep. What makes quantum mechanics especially relevant when discussing life, death, and consciousness is that it challenges our core assumptions about reality's continuity. On some level, almost all physical processes, inside living organisms and inanimate objects alike, can be reduced to quantum terms. The carbon atoms in your DNA, the electrons firing in your brain, all behave as quantum entities, and yet, the transition from quantum to classical behavior, the realm in which objects take on definite positions and the brain supports conscious thought, is a subject of ongoing scientific scrutiny. Quantum mechanics is also astonishingly precise. It underpins much of the technology of daily life. Lasers, computer chips, magnetic resonance imaging machines, and atomic clocks all harness quantum phenomena. Experiments have verified quantum predictions to unprecedented accuracy. For instance, the magnetic moment of the electron has been measured to agree with theory within 1 part in a trillion. And yet, when we move from governed systems, like the simplicity of electrons zipping around an atom, to the messy and warm complexity of life, especially consciousness, most physicists agree the rules get harder to follow in a straight line. Despite that, the intrigue persists. Some scientists hypothesize that quantum effects might operate or even play an essential role in complex biological phenomena, perhaps even in the mind's emergence. Operations within living tissue usually happen amid heat and endless molecular jostling, which tends to wash out delicate quantum effects, a process known as decoherence. Nevertheless, certain cases in biology, like the efficiency of photosynthesis or the navigational abilities of some birds, display hints of quantum coherence at work. So, as you close your eyes, imagine, within you and in every object around you is a world far more mysterious and fluid than everyday reality suggests. A world where probabilities rule, connections transcend distance, and the tiniest particles flicker in and out of potential until we look, or measure, or interact. This is quantum mechanics, and its puzzles set the stage for our gentle inquiry into whether the enigma of consciousness might, just might, intermingle with the physics of the invisible world. As we continue our peaceful exploration, let's softly focus on how quantum phenomena are found within the building blocks of life. For much of the 20th century, scientists thought that living organisms, warm, messy, and full of constant molecular motion, were simply too chaotic for the fragile effects of quantum mechanics to play a meaningful role. After all, quantum events were seen as the silent ballet of the subatomic, confined to cold vacuum chambers and high-energy physics labs. But as researchers turned their attention to life's smallest parts, surprising hints began to emerge that quantum phenomena may, in fact, whisper through biology's most intimate processes. Every living cell in your body is, At its heart, a temple of molecular complexity. Billions of molecules interacting every instant, carrying out the routines of metabolism, replication, and response to the world outside. These molecules, proteins, enzymes, DNA, even the humble water molecules, are built from atoms, and atoms in turn from protons, neutrons, and electrons. At this level, quantum mechanics is not just relevant, it's essential. For example, the very existence of chemical bonds, your body's structural glue, depends on electrons behaving as quantum waves. When two hydrogen atoms bond with an oxygen atom to make water, they do so by allowing their electrons to form shared orbitals, a phenomenon quantum mechanics precisely predicts. But recent research reveals even deeper ways that quantum effects seem to shape living matter. Take photosynthesis, the miracle by which plants and some bacteria capture sunlight's energy and channel it into food. Classical theories long struggled to explain the remarkable efficiency with which light energy, absorbed by chlorophyll, zigzags through protein mazes to reaction centers. In 2007, experiments using ultra-fast lasers showed that the energy, instead of moving along a single random path, seems to explore all possible routes at once through quantum superposition, selecting the most efficient path. This quantum coherence, a hallmark of quantum mechanics, may last for surprisingly long times, even in the biological warmth of a leaf. Another compelling case arises in the navigation skills of migratory birds. Certain species can sense the Earth's magnetic field with an accuracy that defies easy biological explanation. Evidence suggests that birds may employ a protein called cryptochrome in their eyes, creating pairs of entangled electrons. These radical pairs react in ways influenced by the orientation of Earth's field, providing birds with a built-in quantum compass, tiny quantum events literally guiding them across continents each year. Digging deeper, we see that enzymes, those specialized proteins that catalyze nearly every chemical reaction in your cells, may owe some of their remarkable speed to a quantum trick known as tunneling. In quantum tunneling, a particle can slip through an energy barrier it could never overcome by classical reasoning. Certain enzymes, like those breaking down alcohol or making DNA, appear to enable protons or electrons to tunnel and thus speed up reactions far beyond what would otherwise be possible. Could such quantum features play a role in the mind? Some theorists speculate that quantum states could persist for fleeting moments in the brain's microtubules, tiny structures forming your neuron's scaffolding. While controversial, this idea forms part of ongoing investigations into whether consciousness itself might rely on subtle quantum computations or correlations. So far, evidence is sparse and the field is divided, but the possibility keeps scientists watching closely. It is crucial to note that most quantum effects observed in biology concern processes fundamental to life, but not directly consciousness as we experience it. Still, these discoveries have rewritten old scientific dogmas, showing that life's machinery may tap quantum reality in ways yet undiscovered. The warm, wet, ever-active environment of a cell, previously thought to destroy quantum coherence instantly, now appears to sometimes nurture and even utilize it. The numbers themselves are humbling. Roughly 1014, that's 100 trillion, synapses fire in your brain every second. Each of these events relies on molecular machinery, whose ultimate workings depend on quantum rules. You and every living thing in every instant of existence represent an organized cascade of quantum events. A breathtaking dance in which atoms are neither entirely here nor there, and electrons explore many paths until the universe chooses a single outcome, measured and made real by interaction. The presence of quantum mechanics in life's core does not mean every mystery, from consciousness to memory to death, can be simply explained by quantum effects. But it does mean that life and the universe, even at their most basic, are far more intertwined with the odd logic of the quantum world than once suspected. The fact that quantum states can persist long enough, even within a bustling cell, to make sunlight harvestable or allow migration by starlight's guide, speaks to how evolution may have woven the deepest laws of reality into the ongoing miracle of living matter. As you imagine your own cells quietly pulsing and dividing beneath the hush of the night, it's a gentle comfort to remember. The quantum world is not some distant foreign realm. It is the ever-present foundation of life, death, and perhaps the consciousness with which you listen even now. As we drift deeper into our tranquil exploration, it becomes time to softly ask, what is consciousness? This word, so familiar, yet so elusive, sits at the center of age-old debates crossing philosophy, medicine, and science. Is consciousness a kind of energy, an emergent pattern, or merely the byproduct of brain chemistry? Answering this with gentle precision requires an understanding of both neuroscience and philosophical tradition, as well as a look at some of the major hypotheses that continue to shape current research. Consciousness, in the broadest scientific sense, refers to the subjective experience of awareness, the feeling of being awake, of having thoughts, perceptions, sensations, and perhaps even a sense of self. When you listen to a favorite song, recall a childhood memory, or notice the feeling of your breath, that is consciousness at work. This ordinary miracle, this ongoing internal movie, seems intimately tied to the activity of your living brain. Historically, some of the earliest scientific explorations of consciousness occurred in the 19th century. Figures like William James describe consciousness as a stream, continuous, flowing, and always changing. With the advent of modern neuroscience in the latter part of the 20th century, especially with technologies that allowed scientists to record the brain's electrical symphony in real time, our understanding began to shift from philosophical speculation to more concrete, testable reality. At its most basic, conscious awareness in humans appears to rely on the coordinated activity of vast neuronal networks within the brain. Approximately 86 billion neurons communicate through trillions of synaptic connections, forming feedback loops and complex patterns of electrical and chemical signaling. Certain regions, like the thalamus, the prefrontal cortex, and the parietal lobes, are particularly active when an individual is conscious and awake, as opposed to deeply asleep, anesthetized, or in a coma. One prevailing scientific theory, known as the global workspace theory, promoted by Bernard Baars and later Stanislas Dehaene, likens consciousness to a theater where select information is broadcast to many distributed areas of the brain, allowing various subconscious processes, vision, language, memory, to work together. Another influential account, the Integrated Information Theory, IIT, measures consciousness in terms of how much integrated information a system generates. Developed by Giulio Tononi starting in the early 2000s, IIT proposes that consciousness arises from the way information is bound together in a unified experience. According to this theory, the higher the integration, called phi, the richer the conscious experience. Some researchers, like Nobel laureate Francis Crick and Christoph Koch, have sought the neural correlates of consciousness, the minimal sets of brain events and structures required for specific conscious experiences. New tools such as functional MRI and EEG have made it possible to watch, in striking detail, how patterns of firing across brain areas correlate with the intensity or type of subjective awareness a person reports. And yet, for all this progress, the hard problem, famously described by philosopher David Chalmers, remains. How does the objective activity of neurons create the subjective feeling of experience? This explanatory gap, why any combination of biochemistry and electrical pulses should feel like something from the inside, remains unresolved. Some propose that the answer may forever escape reduction to simpler causes, while others work tirelessly, certain that, like many scientific mysteries before, It may at last yield to careful measurement and bold theory. A subset of scientists and philosophers have speculated whether consciousness could be more than a property of biological brains. Might it be an emergent property of sufficiently complex physical systems, even non-biological ones like sophisticated computers? This field of thought, often called panpsychism or artificial consciousness, remains controversial, but it points to our growing willingness to consider consciousness not as a binary state, but as a matter of degree, graded by complexity, integration, and connectivity. For those seeking a quantum link, another set of theories, perhaps most notably orchestrated objective reduction, OR, by Roger Penrose and Stuart Hameroff, propose that consciousness depends on quantum computations or collapses occurring in cellular structures like microtubules. The evidence for this remains tenuous and hotly debated, but it illustrates just how far science is willing to look for explanations that might connect the mysteries of mind to the deepest laws of physics. So, as you relax deeper into your place of rest, know that the question, what is consciousness, is not merely scientific, but deeply personal too. It touches everything you feel, remember, and care about. Whether it emerges solely from neural chatter, or relies on quantum computation, or something we have yet to imagine, remains one of the most open and awe-inspiring questions in all of science. Let's now gently settle into the question: how do we assess whether an entity is conscious? This is not just a matter of philosophical intrigue, but also of immense practical and ethical importance. In medical settings, for example, determining consciousness can decide the course of treatment, resuscitation, and even deeply personal decisions about life support. In research, it shapes everything from animal welfare to the growing dialogue about artificial intelligence. The act of measuring consciousness is thus one of both careful science and profound humility. The traditional starting point in medicine has been behavioral observation. The Glasgow Coma Scale, developed in 1974, provides a clinical rubric for rating a patient's responses across 3 domains: eye-opening, verbal responses, and motor reactions. A fully conscious patient scores highly across all categories, while a person in a coma registers much lower, showing diminished or absent signs of awareness. Yet behavioral tests quickly meet their limits. A person may be temporarily paralyzed, sedated, or physically unable to respond, even as internal awareness remains intact. Locked-in syndrome, for example, is a state in which consciousness may be entirely preserved, despite a complete inability to move or communicate. To probe further, scientists turn to neural measurements. The electroencephalogram, or EEG, records the brain's electrical activity via a series of non-invasive scalp electrodes. In an awake, conscious state, the EEG typically shows fast, irregular oscillations called beta and gamma waves, reflecting the coordinated dance of countless neurons. As a patient falls into deeper levels of unconsciousness, be it sleep, anesthesia, or brain injury, these patterns slow and become more synchronized. In deep coma or brain death, the EEG can go flat, signifying an absence of organized cortical function. Functional MRI, fMRI, emerging in the last 30 years, provides another window into living consciousness by tracking blood flow to active brain regions. Astonishingly, researchers have used fMRI to communicate with certain non-responsive patients, flashing yes or no questions while asking the patient to imagine playing tennis, activating one region, or walking through their house, activating another. When a distinct brain pattern corresponding to the patient's mental image appears, researchers can read out responses, even in the complete absence of physical movement. Such techniques have revealed covert consciousness in a subset of patients, challenging our earlier assumptions about awareness in vegetative states. On the research frontier are attempts to quantify consciousness itself. The most notable effort comes from Giulio Tononi's Integrated Information Theory, IIT, which offers the philosophical and mathematical idea that consciousness is present to the degree that information in a system is integrated and unified. This yields a theoretical measurement, a value called f, pi. But calculating this for a living human brain, let alone deciding on a reliable cutoff, remains a daunting challenge. Meanwhile, in the study of animals, consciousness is inferred from a combination of intricate behaviors, problem-solving, tool use, social communication, and the capacity for pain avoidance. An octopus slipping through a jar lid, a magpie recognizing itself in a mirror, or a newborn human tracking a moving face. All these hint at awareness. Still, science is cautious. Conscious experience, by definition, is subjective from the inside and not strictly inferable from mere behavior or neural activity. Even more provocative is the question of artificial intelligence. When, if ever, might a machine display signs of subjective awareness? Some argue that increasing complexity and connectivity might one day yield machine consciousness, while others insist that something fundamental, some inner spark, is missing from current computers. Experiments, such as the Turing test, which measures a machine's ability to imitate human conversation indistinguishably from a real person, address behavioral mimicry, but not the presence of an inward experience. Ultimately, all attempts to measure consciousness reflect a fundamental tension. We can record brainwaves, observe behavior, and even track blood oxygen changes millimeter by millimeter, yet the one thing we cannot do, at least with certainty, is to see the subjective movie playing for another being. This privacy of experience is part of what makes consciousness such a profound enigma. So, as you breathe quietly in the dark, consider, our tools for measuring consciousness grow more sophisticated each decade, yet always remain, at their core, interpretations. They give us invaluable guidance and at the same time remind us that the deepest reality of awareness may forever resist being completely captured by data alone. This awareness, that the most important things in life are sometimes only barely measurable, connects us all, human to human, scientist to patient, listener to whisperer, and perhaps mind to universe. Let us now drift seamlessly into the profoundly delicate moment of death from a biological perspective. This instant, so shrouded in mystery, emotion, and ritual, can, through the lens of science, be observed as a complex and orderly unraveling of life's architecture. While the event itself may appear abrupt from the outside, on the cellular and systemic level, death is more akin to a sequence of falling dominoes, each affecting the next until the intricate system of life comes gently to rest. In living organisms, particularly in humans, life depends on a continuous supply of oxygen and the delicate orchestration of electrical and chemical signals within the brain and every cell. The brain is arguably the master conductor of this orchestra, its activity responsible not just for movement and thought, but for the very core of conscious awareness. The moment an individual takes their last breath or the heart stops beating, a dramatic change begins, one that scientists and doctors have studied with ever-increasing detail. Within seconds of oxygen deprivation, such as after a cardiac arrest, the neurons in the brain begin to falter. These cells are incredibly sensitive, consuming a large proportion of the body's oxygen and glucose to fuel the constant transmission of electrical signals. Without oxygen, energy stores in neurons are depleted rapidly. Pumps responsible for moving charged ions across cell membranes, the sodium-potassium pumps, start to fail, and with their breakdown, the normal electrochemical gradients that allow for electrical signaling across the neural network begin to dissipate. This loss of gradient leads to a flood of ions into the cells, especially calcium, initiating a cascade that ultimately results in cell injury and death. The longer the oxygen deprivation continues, the more widespread and irreversible the damage becomes. Clinical studies have shown that even after just 4 to 6 minutes without circulation, critical areas of the brain begin to sustain injury. a fact that underpins the urgency with which medical professionals work to restore breathing and heartbeat during emergencies. Beyond 10 minutes, without interventions like hypothermia or life support, the likelihood of meaningful recovery decreases sharply. But even as large-scale brain function ceases, life at the microscopic level lingers for a while. Enzymes continue to operate. Some cells persist in short-lived metabolic activity, and certain networks may even spark faintly before shutting down. Modern research using electroencephalograms, EEG, has revealed that, in rare cases, brief surges of neural activity, sometimes called terminal waves, can occur shortly after clinical death. These waves represent the last synchronized oscillations before the complete disintegration of organized electrical activity. The process is not limited to the brain, of course. Other organs, too, require oxygen and blood flow. The liver, kidneys, and heart cells gradually shut down as the energy currency of cells, ATP, runs out and membranes lose integrity. Cellular death spreads inwards, from areas with the least blood supply toward those with the most. Eventually, all orderly biological processes grind to a halt, and breakdown products begin to accumulate. Carbon dioxide, acids, and reactive molecules signaling the end of active living metabolism. Defining the scientific moment of death has become, in many places, a question of when the brain ceases all integrative activity. In most jurisdictions, brain death, the complete and irreversible loss of all brain function, including the brainstem, is regarded as legal and medical death, even if machines keep the lungs and heart working temporarily. Fascinating statistics lend scale to this transformation. The brain contains about 86 billion neurons, each with thousands of synaptic links, firing countless times a minute. At death, all of these connections become silent, an estimated 100 trillion synapses lapsing into perfect stillness. The average resting human heart beats about 70 times a minute, pumping 5 liters of blood. Yet when the last heartbeat fades, the ripple spreads to every cell, setting the quiet stage for the body's final transitions. The biological moment of death marks the end of integrated physiological function and, according to our best understanding, the end of subjective experience. Yet, as we'll see, this sharp line is only as firm as our tools can measure, and questions linger as to whether there are fleeting echoes of awareness, or even quantum possibilities that might slip softly through before the night is complete. As you ease a little deeper into your breath, know that this quiet unraveling is one of nature's most universal cycles. To observe it scientifically is not to diminish the wonder, but to illuminate how intimately woven together are the threads of chemistry, energy, and, perhaps for a glimmering moment, consciousness itself. As we calmly continue, let's gently illuminate what happens when the organized structure of a living system collapses in death. A phenomenon classical physics calls the breakdown or collapse of classical systems. In life, all the disparate parts of our body work together with exquisite coordination. Billions of cells, numerous organs, and vast molecular machinery sustain an overarching order, keeping us healthy, aware, and able to interact with the world. This harmonious orchestration is what scientists refer to as a classical system, one whose components remain predictable, governed by the well-understood laws of classical physics. When death occurs, this organization falls away. Imagine an elaborate orchestra whose conductor puts down the baton. The music, once beautifully organized, dissolves into disconnected, isolated noises before fading into silence altogether. In the living body, elaborate control systems, our circulatory network, nervous system, and countless cellular feedback mechanisms cease to function as an integrated whole. The boundaries that once kept everything purposeful dissolve, unveiling fundamental shifts in physical processes. Immediately after the cessation of vital functions, your cells and tissues begin to experience profound changes. Classical physics steps in to explain what follows. At the most basic level, gradients of temperature, concentration, and electrical potentials disappear. The membranes of cells, so meticulously maintained during life, become leaky as ATP production halts. Without this chemical energy, pumps embedded in cell walls stop pushing ions in and out, and molecules drift aimlessly toward equilibrium. Loss of order leads quickly to entropy, a measure of disorder, rising within the system. Where life had carved a local pocket of low entropy, high order, death reverses this, with all components trending inexorably toward disarray and eventual dissolution. Outside of individual cells, larger-scale breakdowns occur as organs stop working in concert. Blood, once kept in motion by the heart's rhythmic beats, stagnates, forms clots, and pools under the influence of gravity. Nerve impulses, once the backbone of control and coordination, disperse, no longer initiated and no longer guided by the autonomous nervous system. Muscles, denied the electrical signals and chemical gradients that fueled contraction, stiffen in rigor mortis as calcium ions flow freely, unchecked by the once vigilant pumps. This fate, dictated by the relentless laws of classical physics, is not unique to living systems. Every structured system in the universe, stars, crystals, even weather patterns, eventually succumbs to disorder, their fleeting order replaced by randomness. In biological death, it serves as a poignant reminder of our place in the larger tapestry of the cosmos, organized, animated for a time, and then gently disassembled, molecule by molecule, until none of the original functional order remains. But perhaps most curiously, the moment order breaks apart is when classical descriptions become insufficient for capturing every aspect of what unravels in the transition between life and death. The story of death's aftermath, how gradual, how absolute the dispersal of order becomes, leads us gently into a subtle terrain where quantum questions begin to arise. For instance, as information encoded in the arrangement of molecules disperses, does any quantum-level trace of order remain, or does everything fade irretrievably into classical randomness? This is where the science grows most fascinating. Some hypotheses, as we'll explore, suggest that quantum information, entanglements, correlations, or subtle traces might, in principle, persist beyond the classical collapse of order. In the known universe, however, classical breakdown is where our most reliable tools and knowledge have their firmest footing. Death thus marks the final act in the dance of classical order, and the beginning of what may or may not linger in the strange and elusive reality of the quantum. As you rest more comfortably, it's humbling to realize that the graceful transition from elaborate structure to randomness is not just an end, but also a return. Molecules dispersing into the world, their patterns dissolved, yet their elements recycled in the transformative rhythm of the cosmos. Now let's softly consider a question at the frontier of both physics and philosophy. When life ends and order collapses, what happens to the quantum states within the body? Does the quantum information woven into our cells, molecules, and perhaps even our thoughts simply disappear? This is not only a technical inquiry for physicists, it's also a window onto wider questions of permanence, memory, and the very laws governing the universe. To begin, let's clarify what we mean by quantum information in the context of biology. Every atom and molecule in your body occupies a quantum state, a mathematical description encompassing possibilities of position, energy, spin, and more. These states interact ceaselessly, forming the chemical bonds and reactions that sustain life. What's less obvious is that the specific network of connections between these quantum states, the shared entanglements, subtle correlations, and histories formed by particles, constitutes what physicists call quantum information. In theory, quantum information is special. It cannot be copied exactly, the no-cloning theorem, and under most circumstances, it isn't destroyed but rather spreads out, often becoming practically inaccessible. a phenomenon called decoherence. In living biology, the quantum information is usually contained within the highly ordered and shielded environment of cells. But upon death, as the classical ordering breaks down and the system heats, jostles, and mixes, decoherence takes over, causing the highly organized quantum states to scatter and entanglements to dissolve. Does this mean quantum information is lost? Here, science offers a nuanced view. According to well-established laws of physics, specifically the principle of unitarity in quantum mechanics, quantum information in a closed system is conserved. It's not destroyed, but scrambled into forms that are indistinguishable to any practical observer. In the open, complex system of a dying organism, quantum information flows from tightly correlated patterns into a dispersing cloud of incoherence, mixed irrevocably with the environment. Consider a brain cell at the moment of death. All the quantum states, those delicate arrangements between charged ions, neurotransmitter molecules, and electrons, decohere rapidly. Interactions with surroundings, heat, and the molecular jostle of death scatter the quantum patterns, so no organized memory of the original state remains. The information isn't annihilated, but diffused so thinly into the noise of the universe that it can no longer be reconstructed. This is sometimes compared, in metaphor, to burning a book. The ink molecules and paper fibers remain scattered in ash and smoke, but the meaningful pattern, the story, has all but vanished. On cosmic scales, this dilemma echoes in the famous black hole information paradox. When physicists debated whether information falling into a black hole was truly lost, it led to decades of inquiry and ultimately a widespread belief, championed by Stephen Hawking and others, that even in the collapse and evaporation of black holes, information is not destroyed, but rather transformed, infinitesimally scrambled, yet lurking somewhere in radiation and chaos. By analogy, the quantum information in the body doesn't cease at death. It is redistributed, entangled with the broader universe in a way that is, for all meaningful purposes, lost to recovery. Yet, this scientific safeguard of quantum information conservation shouldn't be confused with survival of mind or consciousness. The brain's information, on the level that creates subjective awareness, is encoded not just in quantum states, but in the intricate dynamic connections and firing patterns among billions of neurons, a complex, adaptive order. When these patterns collapse and decohere, as in death, any conceivable quantum traces are so chaotic that the conscious experience itself, at least as currently understood, is fundamentally erased. Still, there's a gentle wow factor here. Every biological death echoes the grand processes of physics. Matter and energy are preserved, quantum information disperses, and nothing vanishes entirely. It offers a perspective that connects our individual stories with the larger, law-bound flow of the universe, where change is constant, but true loss of information is, on the fundamental level, forbidden. So, as you close your eyes tonight, let the thought rest gently. At the moment of death, the organized quantum states that animated life and mind fall silent. Yes, but their echoes, however faint and diffuse, shimmer forever as part of the great quantum symphony that enfolds all things. Now, as we drift further into the subtleties of the universe, let's explore a foundational concept in quantum mechanics that holds special relevance to our inquiry: the quantum measurement problem. This gentle but profound puzzle not only shapes our understanding of the quantum world, but also prompts intriguing questions about observation, reality, and, possibly, the fate of consciousness as life's currents ebb away. In quantum mechanics, particles like electrons or photons are described not by single definitive states, but by a blend, superposition, of all possible configurations. This blend is mathematically captured in what physicists call a wave function, a cloud of probabilities extending over all futures and states until something happens to select just one. But what determines which outcome becomes real? This question is known as the measurement problem, and it has preoccupied generations of scientists and philosophers. Niels Bohr and Werner Heisenberg, in the formative years of quantum theory, argued that the act of measurement, or observation, forces the wave function to collapse, selecting a single, concrete reality out of all possible options. Before such a measurement, the system remains a mysterious jumble of possibilities, indeterminate and undefined. Solve this gently. What counts as a measurement? Is it the involvement of a conscious observer, the interaction with any sufficiently complex environment, or merely any irreversible recording event in the physical world? This challenge, sometimes called the observer effect, raises philosophical and technical questions. In the famous double-slit experiment, for example, an electron or photon displays wave-like behavior, passing through both slits at once. But if you measure which slit the particle goes through, the act of observation collapses the ambiguity, and the particle behaves as if it passed through only one. It's as if the universe itself decides on a single outcome when watched, but remains fluid and ambiguous when unmeasured. Such ideas have fostered myths that consciousness itself might play a special role in causing quantum outcomes to solidify. Though provocative, most contemporary physicists favor explanations based on decoherence. When a quantum system interacts with the broader environment, even without any conscious being involved, its superposition is so thoroughly entangled and leaked into the world's larger quantum state that it behaves as though it has collapsed to just one outcome. In this view, everyday objects and living creatures appear to settle into a single reality, not because anyone is looking, but because the world is so entangled, noisy, and interconnected that ambiguity cannot last. Nevertheless, unresolved questions linger about exactly how and when quantum possibilities harden into facts, and whether any role for mind or awareness, however subtle, could be woven into this process. Some interpretations, such as the Wigner von Neumann hypothesis from the mid-20th century, flirted with the possibility that consciousness itself is needed to trigger the collapse. Most present evidence suggests, however, that simple physical interaction suffices, but it's a subject that remains open for discussion in both technical and contemplative circles. This connects, softly, to our discussion about consciousness and death. When a living brain, possibly the most complex quantum classical system in nature, ceases to maintain its order, does its pattern of quantum states simply decohere, as with any other system? Or is there any special role that the observation the mind provides might play in its final transition? Most evidence suggests that the dissolution at death is governed by physical processes describable by quantum decoherence. The complex patterns and quantum states scatter, leaving no singular observer to select among outcomes, and the cascade into randomness proceeds inexorably. Astonishing numbers display the scale of all this. In every fraction of a second, countless quantum events unfold in your body, from simple chemical reactions to the firing of neuronal networks. Every moment of living consciousness is, on some level, a unique collapse of possibilities into present experience. When life ends, the capacity for this special kind of quantum classical observation vanishes, but the underlying transitions still play out, as they have since the first moments of our universe. So, as you soften into your pillow, imagine every waking instant is a quiet act of selecting reality from a field of shimmering alternatives, a dance that ceases in its integrated form at death. The quantum measurement problem, mysterious and unresolved, is thus not just a puzzle for physicists. It evokes deep questions about what it means to observe, to be, and to let go. Now, as the night deepens and thoughts slow, let's tenderly explore some of the most speculative and fascinating theories at the boundaries of science. Those that suggest quantum effects might provide a pathway for the persistence of consciousness after death, a concept sometimes referred to as quantum survival. While mainstream science remains cautious or skeptical of such ideas, their very existence showcases the richness of our ongoing curiosity and the enduring mystery of the mind. Among the most discussed is the proposal by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, known as the Orchestrated Objective Reduction Theory, ORC-OR. This hypothesis, introduced in the 1990s, posits that consciousness results not just from classical electrical signaling among neurons, but is fundamentally tied to quantum computations occurring within microtubules, tiny tubular structures that form part of the cell's skeleton, or cytoskeleton, especially abundant in neurons. According to the ORC-OR view, quantum coherence, delicate, synchronized quantum states, can arise and persist fleetingly within the brain's microtubules. These quantum states, it is hypothesized, might underlie moments of conscious awareness. When life ends and classical order collapses, proponents of this view sometimes speculate that the information encoded in these quantum states may not be destroyed, but could somehow persist or become distributed within the quantum fabric of the universe. This connects to broader concepts in quantum theory, such as non-locality and entanglement, where information and correlations can exist across arbitrary distances, seemingly independent of the usual flow of time and space. In this speculative context, some propose that consciousness, or a record of individual experience, might, in theory, be preserved or echoed in some quantum dimension, surviving the death of the biological vessel. Other thinkers have extended these ideas into theories such as quantum immortality, a notion popularized by interpretations of the many worlds formulation of quantum mechanics. This interpretation, first introduced by Hugh Everett in 1957, posits that every quantum event produces a branching of the universe into multiple parallel realities. Under this view, some writers have hypothesized that, for a conscious observer, subjective experience would continue in at least one branch, regardless of what happens physically in other branches, including, astonishingly, after events that would be fatal in most universes. While intriguing, this idea skirts the edges of science fiction and remains unsupported by empirical evidence. Other approaches, such as biocentrism, championed by Robert Lanza, propose that the universe is best understood as dependent on biological observers, and that consciousness itself plays a fundamental, even creative role in bringing reality into being. These ideas, while evocative, are controversial and speculative, often criticized for lacking rigorous testability or clear definitions. Still, these explorations are not without their technical echoes in mainstream physics. The study of information in quantum systems is rigorous, and the principle that quantum information cannot be fundamentally destroyed, even in processes as extreme as black hole evaporation, has deepened our understanding of physical law. Yet scientists emphasize that quantum information is not the same as conscious experience or personal identity. It may persist as a record of correlations or states, but almost certainly not in the organized, meaningful sense that constitutes memory, awareness, or self. To date, no experimental evidence supports the idea that subjective consciousness persists as a coherent quantum state following death. The overwhelming scientific view is that whatever quantum information may linger after the breakdown of the biological brain is so thoroughly scrambled and decohered that it bears no resemblance to the complex, wakeful pattern we know as consciousness. Yet, there is a value in considering these possibilities. They reflect humanity's insatiable hunger for understanding and meaning, the hope that something of ourselves may be woven into the very fabric of the cosmos. These speculative theories, though unwarranted by current data, encourage open-minded inquiry, the willingness to imagine, to speculate, but also to return gently to what science can demonstrate. So now, as you sink into the most restful part of the night, you can rest knowing that, while quantum survival remains an open question at the fringes, it invites a sense of wonder, a bridge between the boundaries of rigorous science and the never-ending creativity of the human mind. As our night journey proceeds, let's softly illuminate the concept of biocentrism and the intriguing shifts it suggests for our place in the universe. Biocentrism is the hypothesis that life and consciousness are not merely accidental byproducts of physical law, but rather fundamental and central features of the cosmos itself. Proposed most prominently by stem cell biologist Robert Lanza in the 2000s, this theory invites us to reconsider the relationship between observer and universe, and in doing so, courts that deep scientific yearning for wholeness and belonging in nature. At the heart of biocentrism is a simple but radical idea. The rules of physics and the physical constants of the universe appear to be not just compatible with life and consciousness, but perhaps are shaped or even defined by them. In this view, the perceptions of conscious beings bring the universe itself into definitive reality, a notion that echoes, in a modern way, the ancient philosophical speculation about mind and matter being intertwined. Drawing on quantum mechanics, biocentrists highlight the way that observation seems to fix reality out of a haze of probabilistic quantum possibilities. The famous double-slit experiment, which we described earlier, shows that light and matter can behave as both wave and particle, but only when a measurement is made does reality choose a specific outcome. This is typically understood in mainstream physics as a result of physical interactions and decoherence, but biocentrists argue that the role of the conscious observer is more primary than conventionally admitted, casting mind as the essential ingredient that brings the universe into full manifestation. The theory extends further. Biocentrists point to the so-called fine-tuning problem, the observation that the constants and laws of our universe appear uniquely calibrated for the emergence and sustenance of life, seemingly against astronomical odds. Where standard science often invokes concepts like the multiverse or anthropic principle to explain this, biocentrism asserts that the presence of life and consciousness is the reason the universe appears as it does. Everything exists precisely because it can be perceived and experienced. What does this mean for life, death, and quantum survival? Some who explore this idea speculate that if consciousness is as fundamental as space, time, or energy, then its cessation in one context, biological death, may not equate to its ultimate disappearance from the universe. Instead, consciousness might persist, reform, or re-emerge in ways that current science is not yet equipped to measure or even conceptualize. In this sense, biocentrism offers a vision of the universe as actively co-created by observers, with consciousness not a momentary spark, but a fundamental enduring property of existence. Critically, mainstream science approaches such claims with caution. There is not yet direct experimental or mathematical evidence that consciousness determines physical reality, or that biocentrism provides testable predictions beyond standard quantum mechanics and cosmology. Many physicists see it as a provocative and poetic interpretation, rather than a scientific theory in the strict sense. The apparent requirement of an observer in quantum processes, for example, can almost always be explained through environmental interaction, without needing consciousness itself to play a special role. Still, the draw of biocentrism remains strong for those who sense, intuitively if not always empirically, that reality's deepest riddles must include the subjectivity of being alive and aware. In this vision, you, the observer, are not a mere passenger, but an elemental part of the story, with perception woven into the very structure of space and time. For those who ponder the persistence of consciousness in quantum states after death, biocentrism offers at least a gentle comfort. The universe may not be a cold, impersonal expanse, but a dynamic field where awareness and existence are inseparable. Even without scientific confirmation, the idea encourages us to appreciate the profound connection between our individual life and the cosmos, and to approach the unknown with a sense of gentle awe. So as you breathe quietly and the world slows around you, remember that to be conscious is, in this philosophical tradition, to participate in the very making of reality, a role as mysterious and central as any the universe can bestow. Let's now softly turn our focus to a particularly evocative hypothesis that has captured imaginations both inside and outside the scientific world: the idea of a quantum soul. This concept asks if there might be something about the nature of consciousness, a unique informational pattern, a subtle organization of quantum states that persists when the physical body comes to rest. It's a bold fusion of ancient spiritual ideas and 21st century physics, inviting us to ask how far we can stretch the laws of science in pursuit of understanding the essence of individuality. The idea of the soul has, of course, deep philosophical and religious roots, appearing in nearly every human culture as a way to explain personal identity, consciousness, and the apparent continuity of self across the changing experiences of life. In the modern era, especially as scientific tools have sharpened our understanding of the brain, conventional explanations have shifted from vitalist soul stuff to more material accounts centered on neural networks and emergent properties. Yet the fascination with something enduring, distinct, even immortal, persists. And in the last few decades, some have wondered if quantum physics might offer a bridge between the old language of the soul and the new science of the brain. One contemporary version of the quantum soul hypothesis draws from the same ideas as the Orc-Ore theory proposed by Roger Penrose and Stuart Hameroff. These theorists suggest that if consciousness arises from quantum processes in neuronal microtubules, perhaps the informational content of consciousness could, at death, dissipate into a larger quantum substrate. The quantum soul would not be a little cloud of vapor or an invisible double, but a pattern of quantum correlations, entanglements, or coherences that escapes classical dissolution. It's important to emphasize that this idea is largely speculative and rests more in the realm of philosophical possibility than experimental science. What, after all, would it mean for a pattern of quantum information to persist? In science, information is precise. It relates to the configuration and correlations among physical systems. Quantum information, in particular, cannot be copied, no cloning, and is exceptionally fragile in the presence of environmental disturbance, a process known as decoherence. When the intricate order of the living brain breaks down, decoherence unfolds rapidly. Any special quantum states linked to conscious experience disperse into random noise. Nonetheless, some theorists suggest that quantum information, being fundamentally conserved in physics, may not simply vanish, but instead delocalizes, perhaps taken up into the physical vacuum or encoded in subtle quantum fields. In this speculative framework, what was once the quantum pattern of a mind might scatter, not destroyed, but diffused across the weave of the universe. Could this be a scientific version of the soul? Or is it merely a poetic reformulation of dissolution, a transformation from intricate personal order to cosmic anonymity? It's worth noting too that mainstream neuroscience and physics remain for now unconvinced. No empirical evidence, no experiment, no reproducible measurement has found persisting quantum patterns connected to memory or identity after biological death. Most scientists interpret the laws of conservation of quantum information as describing the fate of subatomic arrangements, not consciousness, as a meaningful, living reality. The processes that create mind, the coordinated electrical and chemical signaling of billions of neurons, do not, as far as research currently shows, leave a coherent or retrievable trace when the classical order dissolves. Yet for those seeking meaning in the face of mystery, the quantum soul idea offers a sense of continuity. It suggests, at least metaphorically, that each life's unique tapestry of information, woven for a time into self and subjectivity, is never wholly destroyed, just transformed, scattered, merged with the universe at its deepest level. This vision bridges ancient intuitions and modern physics, offering an image of connection across time, space, and perhaps, in some unspecifiable sense, existence itself. So rest now in the thought that, while science has no clear answer, the notion of a quantum soul speaks deeply to our wonder, reminding us that the boundary between what is known and unknown may be as rich, subtle, and endlessly fascinating as consciousness itself. Let us now gently explore the critiques and controversies that swirl around the idea of quantum survival and the persistence of consciousness after death. In the peaceful spirit of scientific inquiry, it's important to acknowledge both the allure and the skepticism surrounding these speculative notions, and to understand why the majority of scientists and philosophers remain deeply cautious about claims that consciousness can persist in quantum states beyond the dissolution of the biological brain. One of the first, and perhaps most fundamental critiques, hinges on the problem of scale. Quantum effects, while dominant in the subatomic world, tend to vanish rapidly as systems become larger or interact with their environment, a phenomenon called decoherence. Warm, wet, and noisy environments, like those in living brains and bodies, generally suppress quantum coherence on timescales as short as femtoseconds, quadrillionths of a second. Most neuroscientists and physicists assert that the electrical activity and connectivity patterns that give rise to consciousness operate at a scale and complexity where quantum effects wash out almost instantly, replaced by classical physics. This view is buttressed by decades of research tracing the workings of perception, memory, decision-making, and selfhood to networks of neurons firing in classically predictable patterns. Secondly, even if fleeting quantum phenomena did play a role in sustaining consciousness, most critics argue that the highly organized patterns, encoding subjective experience, personal memory, and identity, would not survive the catastrophic decoherence that occurs at death. The collapse of the body's ordered structure and the breakdown of neural circuits would scatter whatever quantum information might exist, scrambling it far beyond retrieval or meaningful reconstruction. In this light, the conservation of quantum information in physics is taken by most scientists to refer to raw physical data, not the persistence of mind or awareness per se. A further controversy relates to the interpretations of quantum mechanics itself. While certain hypotheses, like biocentrism or the role of the observer, highlight the weirdness of measurement and the possible primacy of consciousness, the overwhelming consensus is that quantum phenomena do not require a conscious observer to resolve superpositions into concrete reality. Modern approaches, like decoherence theory, successfully explain the apparent collapse of quantum states through environmental interaction, not through observation by a sentient being. This helps separate the provocative idea of consciousness causing reality from the more evidence-based conclusion that measurement, in quantum terms, simply reflects physical change recorded somewhere in the system. Critics also highlight a lack of empirical support. Despite many experiments probing quantum processes in biology, including studies of photosynthesis, avian navigation, and enzyme activity, none have demonstrated quantum effects linked to memory, consciousness, or subjective awareness in a testable, repeatable way. Proponents of ideas like the quantum soul, or OR, are often challenged to present direct evidence, measurements or outcomes that could confirm or falsify their claims under controlled conditions. There is also a philosophical critique, sometimes called the category mistake. This argues that consciousness is an emergent phenomenon of highly integrated and regulated neural activity, one not directly translatable into quantum terminology. Asking whether subjective awareness persists as quantum information after death, by this account, is a little like asking whether the song of a violin persists after you dismantle the instrument and scatter the pieces. The basic elements remain, but the structure, the meaning, and the emergent properties that created the song, like the mind, are lost. The field, of course, is still young, and the allure of quantum mystery continues to inspire ongoing debate. New discoveries in quantum biology neuroscience, and the study of consciousness may one day nudge the boundaries of what we believe possible. But at present, the prevailing scientific opinion is that while quantum physics underpins all things, there is no evidence to support the idea that consciousness, in the sense humans knowingly experience, persists as quantum information, or migrates beyond bodily death in any structured or recoverable form. So as you sink deeper into relaxation, consider that the skepticism and controversy themselves are signs of a healthy science, one that holds wonder and evidence in delicate balance, trusting both curiosity and the rigor of proof. The quantum world may still hold surprises, but for now, the persistence of consciousness after death remains an open question, best faced with both humility and a patient, watchful mind. Now let us drift quietly into the subtle world of laboratory research. What have key experiments taught us about the tantalizing connections or limits between death, quantum processes, and consciousness? At this gentle intersection stands a blend of established science, lively curiosity, and the enduring humility that comes with peering into mysteries we can barely touch. To date, no experiment has definitively demonstrated that consciousness relies on, or is preserved by, quantum phenomena after the breakdown of the bodily brain. However, a diverse set of studies have helped clarify what quantum effects are present in living systems and just where their influence may end. Let's softly review some of these noteworthy endeavors. Much of the proven quantum biology work has focused not on brains, but on processes like photosynthesis, magnetoreception in birds, and enzyme catalysis, domains where quantum coherence and tunneling have been detected and measured. These results from ultrafast spectroscopy and molecular tracer experiments demonstrate that quantum effects do persist for tiny stretches of time and distance, even amid the thermal complexity of living cells. But crucially, these phenomena seem confined to specialized biochemical machinery rather than the vast, ever-shifting networks that underpin conscious thought. Shifting to neuroscience, scientists have devoted decades to imaging, measuring, and perturbing the awake, unconscious, and dying brain, searching for quantum fingerprints. Using tools like EEG, MEG, magnetoencephalography, and fMRI, researchers have mapped the flow of electrical and metabolic activity as it waxes and wanes with awareness, sleep, anesthesia, and brain injury. These studies reveal intricate, large-scale patterns, global oscillations, network synchrony, modular feedback, all utterly explainable using established physics and chemistry. No necessary recourse to quantum superposition, entanglement, or tunneling has emerged in the creation or loss of subjective awareness. One influential set of experiments stems from attempts to test the Orkowa theory's prediction that quantum coherence might persist in warm neuronal microtubules. In a series of studies from the 2000s through the 2020s, physicists and neuroscientists examined whether any long-lived quantum states exist in brain tissue. The results so far have been negative. Microtubules, though highly structured, seem unable to maintain quantum coherence for more than a fraction of a nanosecond before decoherence. Randomizing interactions with water molecules and ions wipes out orderly quantum patterns. Experiments at the threshold of death have also revealed surprising phenomena, such as terminal surges of organized brain activity just before biological silence, documented by EEG in both humans and animals. Though mysterious, these late waves of electrical synchrony have so far been interpreted as the natural consequence of dying neural networks collapsing, rather than as evidence for quantum persistence or the escape of soul-like information. On the quantum side, laboratory research has illuminated the durability of quantum information in isolated, carefully controlled systems such as ions, photons, or superconducting circuits. Physicists have demonstrated quantum teleportation, entanglement over hundreds of kilometers, and even error-corrected quantum memory. But these achievements, with all their wonder, rely on extreme isolation, vacuum chambers, or cryogenic temperatures. dramatically different from the fiery chemical churn of living brains, especially at the end of life. Another fascinating direction has been efforts to detect so-called quantum signatures in radical pairs, molecular complexes relevant to avian magnetoreception, using techniques such as spin resonance spectroscopy. These signatures confirm that quantum coherence can contribute to information processing at the molecular level. But there has been no indication that such mechanisms contribute to self-awareness, memory, or experience. Scientists have even explored the possibility of quantum-level changes at death, using particle detectors sensitive to subtle emissions. For instance, in rare case report studies of terminally ill patients, researchers have measured for sudden losses of physical mass or energy at the moment of death, with the hope of finding evidence for some form of information release. These studies, popularized by sensationalist interpretations, have found no reproducible effect, and most are regarded skeptically due to confounding variables. These experimental frontiers, while yielding no support for the survival of consciousness as a quantum phenomenon, do bring us closer to understanding both the strength and the limitation of current scientific paradigms. They show again and again that the phenomena of mind and death are deeply rooted in classical neurobiology, with quantum effects acting as the distant foundation, the canvas rather than the painting itself. In sum, the research journey continues, but at each step, the mysteries grow subtler, not simpler. As you settle further into darkness, consider how each experiment, whether confirming a quantum effect or quietly revealing its limits, brings us closer to appreciating just how exquisitely tuned, and yet how ephemeral, the music of consciousness truly is. Now let's ease our focus onto a deeply human subject, one that touches the borderland between life and death, near-death experiences, or NDEs. Scientific study of NDEs offers a rare window into the last flickers of consciousness and invites us to ponder what, if anything, might persist as the boundaries of life dissolve. As always, our approach is gentle, careful, honoring both the wonder of these accounts and the rigor required for understanding them. Near-death experiences have been documented across cultures and centuries. They typically occur in situations of extreme physiological crisis, cardiac arrest, profound trauma, or medical emergencies where vital functions stop or drop perilously low. Common features are reported by many people: sensations of floating above one's body, seeing lights or tunnels, encounters with loved ones, feelings of profound peace, or a rapid review of one's life. Some describe visiting realms that seem more real than waking life, while others recount a distinct sense of existing outside time and space. Since the 1970s, researchers have approached NDEs scientifically, with Raymond Moody's book, Life After Life, sparking formal inquiry. In the decades since, studies have multiplied, especially with improvements in resuscitation medicine, allowing more people to survive events like cardiac arrest. A major finding is statistical. About 10% to 20% of survivors of cardiac arrest, who have been technically dead for up to several minutes before revival, report some features consistent with NDEs. A leading research effort is the AWARE study, Awareness During Resuscitation, led by Dr. Sam Parnia and colleagues. This ambitious multi-center trial has enrolled thousands of cardiac arrest survivors. In addition to questionnaires and interviews, some hospitals placed visual targets only visible from near the ceiling to test whether those who described out-of-body experiences could report verifiable visual information. To date, corroborated out-of-body, the perceptions are vanishingly rare, with most subjective experiences not matched by external events. Neuroscientific explanations for NDEs focus on what occurs in the brain as blood flow and oxygen drop to critical levels. As we have explored, neurons are extremely sensitive to loss of oxygen, and their electrical signaling collapses rapidly. Before all organized function vanishes, however, there can be a brief period of highly synchronized activity, a surge of electrical oscillations across wide regions of the cortex. Some animal studies, as well as human case reports, document such terminal bursts or spreading depolarizations, waves of electrical activity that arise just before complete shutdown. These bursts may generate vivid sensations, hallucinations, and dreams. Similar experiences can arise in patients even without brush with death, such as those experiencing fainting, syncope, extreme stress, or certain seizures. Drugs that disrupt the balance between inhibitory and excitatory signals, like ketamine, can induce experiences closely matching NDEs, including out-of-body sensations and powerful emotional visions. These findings suggest that NDEs are not evidence of consciousness leaving the body, but rather reflect the dying brain in its final, chaotic attempts to synthesize experience. Still, profound questions remain. People who return from NDEs often describe them as transformative, carrying lasting changes in attitudes toward life, death, and spirituality. For researchers, this personal meaning is as worthy of study as the underlying biological processes. Yet, when it comes to the central question, does consciousness persist in quantum states after biological death? Science has so far found no evidence linking NDEs to quantum survival. The vast bulk of research points to NDEs as phenomena emergent from brain activity under stress, not as indicators of awareness continuing independent of the body. Fascinatingly, these experiences do highlight the resilience, adaptability, and complexity of consciousness at the edge of its classical basis. They remind us that the mind's final moments are often rich and mysterious, filled with patterns both neuroscientific and deeply personal. So, as you relax more deeply, let this knowledge gently rest. NDEs are powerful, meaningful, and biologically explainable. They speak to the luminance of mind, but so far, not to its quantum endurance beyond life. Let's now turn our attention, in this gentle midnight hour, to the interplay between memory, quantum effects, and biology. Memory, the ability to encode, store, and retrieve information across time, is one of the great wonders of consciousness, shaping who we are from moment to moment. Some have speculated that quantum processes might underlie or even enable those moments when recollection seems instantaneous, vivid, or even inexplicably detailed. What does current science reveal about this relationship? To begin, let's explore how memory functions in the brain according to well-established neurobiology. The formation of memory relies on chemical and electrical changes at the synapse, the junctions you have between neurons. When you perceive or experience something, patterns of neural activity ripple through vast networks. These signals stimulate the growth or removal of synaptic connections, a process called synaptic plasticity. On a molecular scale, this involves the movement of calcium ions, the release of neurotransmitters, and the structural modification of proteins and membranes. One key process known as long-term potentiation, LTP, first studied in detail in the 1970s, occurs when repeated stimulation of certain neural pathways makes those synapses stronger, more likely to fire in future. LTP and its complement long-term depression, LTD, appear fundamental for storing memories. These processes are, on the surface, entirely describable by classical physics and chemistry, molecular cascades, gene expression, and changes in the shape and function of synapses. But could there be more beneath the surface? Interest in possible quantum contributions to memory often centers on several lines of thought. The first arises from the question of brain speed. Some cognitive phenomena, such as abrupt insight or the virtually instantaneous association of ideas, seem swifter than what one might expect from the serial, step-by-step transmission of information. Some scientists and philosophers have wondered if quantum superposition and coherence, where information could, in theory, be processed in parallel pathways, might explain these rapid cognitive leaps. The most developed speculation in this area, again, involves microtubules within neurons. Proponents of the Orkawa theory suggest that these structures may sustain quantum states lasting long enough to influence synaptic changes and thus memory. However, as we have seen in earlier sections, rigorous experiments have cast doubt on this proposal. Quantum coherence within brain microtubules, if it occurs at all, seems too fleeting to impact neural activity on meaningful timescales. Outside the microtubule hypothesis, some researchers have looked for quantum signatures in animal learning or perception, testing, for example, if entanglement or superposition can affect how organisms respond to novel situations. Thus far, no evidence has emerged that quantum effects drive memory processes in any species, human or otherwise. This brings us to a fascinating distinction in contemporary science. While memory and sensory signal transduction absolutely depend on molecules and elementary particles that themselves obey quantum laws, the properties required for robust memory, reliability, retainability, and retrievability, seem better served by classical rather than quantum systems. Quantum states are exquisitely sensitive, prone to decoherence with the slightest disturbance. The brain, by contrast, favors chemical and structural patterns precisely because they are stable over time, resistant to noise, and tolerant to the relentless jostling of biological systems. Supporting this picture, computational models, imaging studies, and even direct neural recordings show that memory formation, storage, and recall can be explained in terms of well-understood physical and chemical changes at the synaptic and network level. While some recent efforts in quantum computing explore the potential for encoding information in quantum systems for artificial brains, nothing analogous has been identified in the human nervous system. Researchers have also probed deeper biological mysteries, such as whether quantum tunneling plays a role in receptor activation, or if entanglement is ever observed in distributed brain processes. The answer remains, for now, negative. Most experts agree. There is no direct evidence supporting memory as a quantum effect, and plenty supporting its classical, biological basis. Still, there's a gentle wonder here. The sheer complexity of brain architecture is staggering. Tens of billions of neurons, hundreds of trillions of synapses, each a natural miracle of information processing. While quantum rules quietly underpin every physical event, it appears that life, by evolution and necessity, has settled on classical mechanisms for the most precious faculty of memory. So, as you drift even deeper, reflect gently that your memories, fleeting, vivid, mysterious, are born of biology's classical resilience, not fragile quantum states. What makes them reliable is not the strangeness of the quantum world, but the grace and stability of molecular and cellular life. Now, in the gentle hush of this unfolding night, let's relax into the questions that swirl around information theory, conservation, and the fate of information after death. Information, in the scientific sense, is more than just memory or thought. It's the pattern, distinction, and structure woven into systems, the differences that make a difference. When we ask if something of us might endure beyond biological death, what we are really asking, in one important sense, is, does the information that made you persist somewhere, somehow, in the universe? Let's begin by understanding information theory. Founded in the mid-20th century by Claude Shannon, information theory set out to systematically measure communication, how much order or choice a signal can carry, how reliably it can be transmitted, and how noise might distort it. In biology and physics, this becomes the study of patterns, the way DNA encodes genetic blueprints, or how synaptic connections in a brain encode experiences, knowledge, and ultimately, aspects of personal identity. Within physics, another landmark principle emerged: the law of conservation of information, especially in quantum mechanics. In simple terms, most physical processes, even those as fiery as stars or as mysterious as black holes, do not destroy information. Instead, information is thought to persist or become scrambled, hidden, or transformed, but never truly erased. This idea grew out of puzzles like the black hole information paradox, which troubled physicists for decades until calculations, helped along by Stephen Hawking, Leonard Susskind, and others, suggested that information swallowed by a black hole might ultimately be preserved in subtle, scrambled patterns in Hawking radiation. Bringing this back to the human scale, every brain is a universe of information. Neurons' firing patterns, the shape of their connections, the timing and strength of their signals. At death, all the exquisite patterns of connectivity and activity that encoded your sense of self, memory, and experience begin to unravel as metabolism ceases and order collapses. Classical information, the specifics of your neural networks, begins to degrade. Quantum information, embedded in the positions and states of particles, is rapidly dispersed by decoherence and environmental interaction. Here's where scientific nuance enters. From a physics perspective, the information isn't destroyed. Instead, as the body falls apart and chemical reactions race toward equilibrium, all the microstates, the arrangements of particles, and the quantum entanglements present within the body are mixed with the environment. Just as the air's molecules scatter the pattern of a book burned to ash, the information about the book's original words is, in principle, still present in the arrangement and movement of all those molecules. In practice, though, the meaningful pattern, the part that makes it a story or a mind, is lost for all conceivable purposes. Information theorists call this dispersal into noise. It is a transformation from highly organized, locally accessible information to diffuse, unrecoverable background. The universe, for all its conservation laws, does not guarantee the survival of particular structured meaning. Instead, it is exquisitely effective at preserving only the raw bits, the record that something was, not what that something meant. Some thinkers, including those who work at the intersection of physics and philosophy, have speculated whether there might be loopholes, mechanisms for the persistence of structure, identity, or awareness at the quantum level. Could there be, for instance, a quantum hologram of the conscious mind, encoded in spacetime or fields? To date, experiments and theory suggest this is possible only in the most abstract and mathematically remote sense. No pathway has been found from the dispersal of physical information at death to the continuity of individuality or lived, subjective consciousness. Yet there are fascinating facts that bridge scales. The human body, over a lifetime, processes information at rates rivaling modern supercomputers, an estimated 1018 to 1019 operations per second in brain cells, and trillions of bits of genetic information copied and maintained by cell division. This ocean of structure is breathtaking, and its dispersal at death reminds us that life is fundamentally an active process of resisting entropy and preserving islands of information in a vast, shifting sea. So, as you settle further into this quiet evening, let the science rest gently. The information that makes up a living brain does not vanish at death, but it becomes so thoroughly entangled with the universe's background noise that, for all meaningful purposes, the individual pattern, the self, is gone. What persists is not a mind, but a record, as faint as the photon's shadow from a star that burned out long ago. Now, as the night air grows quieter, let's drift into one of the most profound analogies science has ever provided: the black hole information paradox. This famous question in theoretical physics draws surprising parallels with our own deepest wonderings about the fate of information, be it the history of stars or the intricate patterns of a conscious brain. When order collapses and a system vanishes from view, black holes are among the universe's most enigmatic phenomena. They arise when massive stars exhaust their fuel and gravity crushes their cores to a point so dense that not even light can escape. For much of the 20th century, physicists accepted that anything falling into a black hole, be it matter, energy, or information, was lost forever, wiped from existence at the event horizon. Yet, in the 1970s, Stephen Hawking's discoveries added an incredible twist. Black holes can slowly lose mass and energy through Hawking radiation, eventually evaporating completely over enormous timescales. This realization raised a terrifying possibility. If a black hole can evaporate, what happens to the information about everything it once consumed? If the radiation escaping from a black hole contains no trace of the structure or history of what fell in, then information, according to quantum theory, would be destroyed. But quantum mechanics holds, almost as a sacred law, that information cannot truly be erased. It can change form, scramble, or distribute, but must remain somewhere in the universe's fabric. This apparent contradiction, the information paradox, sparked decades of debate and vibrant research. As the 1990s and early 2000s unfurled, theorists like Leonard Susskind and Gerard Tufte developed the holographic principle, suggesting that the information inside a black hole could be imprinted on its surface, the event horizon, much as a hologram records a three-dimensional image on a two-dimensional surface. By the 2010s, most physicists agreed that, despite the confusion, mathematical consistency demands that the information swallowed by a black hole is not wiped clean, but encoded in the outgoing Hawking radiation in ways still being deciphered, a subtle but crucial preservation, even as the system collapses. What then does this teach us about life, death, and consciousness? The analogy is gently illuminating. In a sense, the living brain, rich with structure and pattern, is like a miniature universe harboring extraordinary information. At death, the dynamic order of experience collapses, much as a star's core falls into a black hole. The patterns that once defined a conscious being are dispersed, just as the information of the collapsing star is thought to be scattered by Hawking radiation. Crucially, while the raw information may not be destroyed, its meaning, the organization, the woven story of the conscious self, is lost. The data may be encoded in the universe's background or in the interacting quantum fields, yet it is so scrambled and diffuse that it bears no resemblance to the coherent, living mind that once animated it. The black hole analogy gently clarifies the difference between rudimentary information conservation and the persistence of identity or awareness. Physics may promise that the bits are not lost, but it offers no guarantee that the narrative, the self, or the subjective experience will survive this ultimate scrambling. Sometimes, in the search for reassurance or continuity, it helps to see that such fundamental puzzles are not personal, they're cosmic. The universe treats collapsing stars, dying cells, and the fate of all patterns with the same implacable rules. Entropy rises, structure dissolves, and only the faintest echoes of the original order remain. So as you rest, feel the connection. Just as the universe's deepest mysteries find their way into the fate of black holes, so too does science's greatest humility enter our contemplation of the end of conscious experience. In both cases, the message is softly profound. Nothing is truly lost. Yet what matters most to us, the rich tapestry of living order, dissolves into the quiet grain of the cosmos. Shall we now let our thoughts softly wander into the realm of possibilities opened by the many worlds interpretation of quantum mechanics? This extraordinary perspective offers an imaginative yet rigorously developed framework that radically rethinks the consequences of quantum events, not only for particles and atoms, but in extraordinary thought experiments, perhaps even for consciousness itself and the puzzle of survival after death. The many worlds interpretation, proposed formally by physicist Hugh Everett III in 1957, posits that whenever a quantum event with multiple possible outcomes occurs, the universe doesn't choose just one. Instead, all possible outcomes happen, but each in its own branching world or distinct history. In this picture, the universe is forever splitting, creating a vast, possibly infinite multiverse of alternative timelines. Every quantum measurement, every roll of the dice at the smallest scale, launches a new cascade of realities, each just as real as the one you experience. In traditional quantum mechanics, the wave function, the mathematical object describing quantum possibilities, collapses to a single outcome when observed. Many worlds eliminates this collapse, instead suggesting the wave function continues to evolve smoothly and deterministically. What we perceive as a single, definitive reality, an outcome chosen, is simply one branch among uncountable others, with equally plausible versions of ourselves experiencing each possible result. How does this relate to the question of quantum survival after death? Some speculative thinkers, riffing on the many worlds interpretation, have pondered whether a version of you might continue in another branch, even if events in our perceived reality end in biological death. For instance, in the quantum suicide thought experiment, an observer's consciousness appears to survive lethal events in at least one branch of the ever-dividing multiverse, leading to the mind-bending idea of quantum immortality. In this framework, subjective experience would always find itself in the branch where survival continues, however improbable. Thus, in some hypothetical extrapolations, consciousness never fully encounters non-existence. It merely hops among surviving versions, indefinitely. It's important to approach these possibilities with a clear scientific lens. There is no experimental evidence that subjective awareness hops between branches, or that memory and identity move independently of physical process. The many worlds interpretation, while mathematically robust and increasingly embraced by some branches of theoretical physics, does not in itself imply survival of the mind past the end of brain function in any meaningful way. The continued existence of alternative versions of you does not mean that your personal consciousness experiences an unbroken story. Rather, it describes a cosmos unimaginably rich in possible outcomes, all realized but fundamentally separate. Nonetheless, the sheer scope of this interpretation is breathtaking. Its mathematics is used to model quantum computation and certain cosmological questions, and its philosophical implications have fueled decades of debate about choice, destiny, and the meaning of identity. As for death, the many worlds view whispers that every moment of collapse is simultaneously a moment of branching, with every quantum event birthing new universes. If the universe truly operates this way, it links your fate, to a degree, to an endless proliferation of alternative selves. It is a vision of nature where nothing is ever truly finalized. Creativity and possibility abound at scales far beyond our individual experience. So, as you drift deeper into relaxation, let the notion of many worlds gently stretch your imagination. It challenges our ordinary assumptions about beginnings and endings, yet offers no easy comfort about what it means to truly persist, or to be. It is a grand reminder that reality is, at its root, stranger, vaster, and more open-ended than even our wildest dreams can contain. As the night deepens, let's quietly reflect on the limitations of our current understanding, those boundaries that science, with all its careful rigor, cannot yet cross when it comes to uniting quantum physics and consciousness. Recognizing our limitations is not a mark of defeat, but rather a gentle admission that some mysteries are still unfolding, waiting for the tools and insights of future generations. One major limitation stems from the immense complexity of consciousness itself. Though neuroscience has mapped countless circuits, regions, and feedback loops within the brain, the so-called hard problem, how physical processes generate subjective experience, remains unsolved. Even with advances in imaging and computational modeling, we still lack an objective measure or mathematical theory of consciousness that seamlessly bridges the experiential and the physical. Contemporary theories, such as global workspace theory or integrated information theory, offer valuable insights at the systems level, but do not connect down to the quantum fabric in a way that can be rigorously quantified or tested. From the quantum perspective, our principal challenge is decoherence. Quantum effects in biology are exquisitely fragile. They dissipate almost instantly in the warmth and turbulence of physiological environments. While quantum mechanics certainly underpins the chemistry of life, any subtle quantum states that might conceivably influence large-scale phenomena like thought or memory are believed to decohere long before they could shape or preserve conscious experience. The timescales of quantum coherence are measured in femtoseconds or less, while cognitive processes operate in milliseconds and up. At present, there is no evidence for brain structures that would shield quantum information long enough or orchestrate quantum computation on meaningful scales. Experimental limitations are also profound. Scientists have made great strides in recording the activity of neural circuits down to single-cell levels, as well as measuring quantum effects in biological molecules. But directly linking any signature of quantum behavior to the emergence or persistence of subjective consciousness remains beyond our technical reach. Efforts to probe the AUK-OR theory or to detect unique quantum effects in neural microtubules have so far yielded negative or inconclusive results. Measurements of memory, perception, and decision-making continue to align with classical models of brain function. Compounding these empirical gaps is the question of interpretation. Quantum mechanics offers several models: many worlds, Copenhagen, objective collapse, decoherence, and more. But none are universally accepted, and all have serious philosophical as well as practical limitations. Whether quantum measurement truly requires an observer, or whether consciousness itself counts as a form of fundamental measurement, remains an open and heavily debated question. Without consensus here, bridging quantum science and subjective experience stays a matter of speculation rather than testable theory. A further limit is the problem of defining what would truly count as evidence for the persistence of consciousness after death. Most scientific models depend on reproducibility, measurability, and objectivity, while the phenomenon in question is, by its nature, private, subjective, and fleeting. Attempts to correlate out-of-body experiences, terminal lucidity, or quantum information release at the moment of death run up against ambiguity, anecdote, and the vast complexity of brain shutdown. Finally, there remains a fundamental humility in science. Every discovery generates new questions, often deeper and more beautifully perplexing than those that came before. The barrier between quantum mechanics and consciousness may be more than just technical. It could signal that new frameworks, potentially beyond both current physics and neuroscience, will be needed to unravel the mysteries of experience and its possible fates beyond life itself. So, as you rest more deeply, let the vastness of what we do not know feel gentle rather than daunting. In the spaces between certainty, you are standing, softly and bravely, within the frontier where tomorrow's most profound insights may yet emerge. As we travel further into the peaceful terrain of this unfolding science, let's gently contemplate a very personal question. If quantum survival were possible, would it truly mean that you, your sense of self, memory, and identity, would survive? The idea is at once deeply fascinating and quietly unsettling because it touches on the essence of what it means to be an individual, not just a pattern of matter, but an unbroken thread of experience. Personal identity, in the view of neuroscience and psychology, emerges from the unique, ever-changing web of connections, memories, habits, and feelings formed by your brain and body. You are not just a sum of base particles, but the history of their organization, the way information flows, the strengthening and weakening of synaptic pathways, and the cascade of experiences that paint the ongoing portrait of self. This structure is staggeringly complex, approximately 86 billion neurons and trillions of interconnections, each shaped by genes, environment, and choice over time. In the quantum realm, as we've seen, information is preserved at the most fundamental level when particles interact. Nothing is ever destroyed, only transformed. If every interaction leaves a mark, then the pattern of you leaves an imprint on the universe, however brief. But this is not the kind of continuity most people mean when they long for survival after death. Scientific evidence points to a stark truth. The organization that supports awareness, dynamic, highly sensitive, and ever-shifting, is swiftly lost as the brain's structure and function collapse. Quantum information persists, but so thoroughly scattered that its original pattern becomes unrecoverable from the background static of the universe. Now, some theories, like many worlds or the notion of a quantum soul, imagine that alternative versions of you could continue to exist under different circumstances, each with their own trajectory. But these versions are fundamentally distinct. The version that experiences a world where you continue is quantum mechanically, not you as you know yourself, but another self who never quite faced the same end. The sense of continuous, unified consciousness that anchors your life story would not leap seamlessly between quantum branches or scattered information clouds. The narrative thread, memory, feeling, and point of view appears to require the uninterrupted, coordinated activity of a living brain. Philosophers have long wrestled with analogies to clarify this issue. Consider the ship of Theseus. If you gradually replace every plank on a ship until none of the original remains, is it still the same ship? Or think of a book whose words are scattered randomly across thousands of pages. The ingredients still exist, but the story cannot be read. In the quantum case, the raw bits of your brain's information are scattered, not erased, but the narrative itself, the selfhood that remembers, desires, and feels, falls apart with the loss of order. This matters for how we interpret claims of survival. Even if quantum effects could preserve information, or if the universe holds endless possibilities where something like you continues, the personal identity you experience is rooted in classical continuity, an ongoing chain of physical and experiential links. Without this, there is no meaningful sense in which you endure beyond biological death. Of course, there is still poetic resonance in the idea that our particles, our informational footprints, are never lost in the grand ocean of the cosmos. They are recycled by physics, remembered by entropy, and woven into new patterns. But the unique, first-person view that is your consciousness, the singular perspective from inside your own experience, appears as ephemeral as the lightning stroke, fiercely real while it dances, forever transformed when it subsides. So, as you settle into gentler thoughts, let this awareness bring both humility and comfort. The science so far suggests that to survive in a quantum state would not be to remain yourself, but to leave a beautifully intricate trace, one more thread in the endlessly unfolding fabric of reality. Now, as we approach the gentle final turns in our journey, let's reflect softly on why these questions matter, how exploring the possibility of quantum survival and the very mysteries of life and death can quietly shape the way we live and meet uncertainty. Even without firm answers, the act of curiosity itself enriches our experience, illuminating the profound strangeness and beauty of simply being. From the earliest stirrings of human thought, pondering the fate of consciousness after death has inspired philosophy, art, religion, and eventually, science. We yearn to draw meaning from our existence, to understand if there is an enduring story behind the fleeting days and moments that make up a life. For some, science's current stance, that memory, awareness, and selfhood are grounded in the living brain and dissolve with its collapse, feels sobering, even unsettling. Yet, for many others, this knowledge can also bring a kind of peace, a reminder that our aliveness is an irreplaceable and awe-inspiring phenomenon, made even more precious by its impermanence. The questions of quantum survival ask us to hold two perspectives in balance. On one side stands the rigor of science, its humility, patience, and reverence for evidence. Here, we find skepticism toward claims of persistent consciousness, paired with a sense of wonder at the subtlety and richness of the quantum world. On the other side rests our psychological and existential need for hope, continuity, and connection. It's natural to wish for something enduring, perhaps a pattern of information, an echo, a branch of self that persists onward, even as the current fades. The act of grappling with these questions can change the way we approach life. Consider, if the continuity of consciousness is truly bounded by life's orderly pattern, then each day becomes more radiant, more meaningful for its singularity. Every moment of awareness is unique, born out of a universe of possibility, shaped by uncountable atoms and quantum events, and yet dissolved just as gently as it arose. In this perspective, uncertainty itself becomes a companion, not an adversary. Rather than fearing the unknown, we may find the courage to accept it as intrinsic to existence, a space where creativity, compassion, and deep presence can flourish. Even for those who hold to religious or spiritual narratives about the afterlife, the scientific story of matter, energy, and information conservation need not diminish wonder or hope. Instead, it grounds these mysteries in a shared reality, linking our brief lives to the vast ongoing cycles of transformation that underlie everything. We know that the atoms in our bodies will return to the earth, the stardust and molecules recycled for future forms of life, and perhaps, if one stretches imagination, a faint echo of our informational pattern will continue in the endless rearrangement of the cosmos. To approach the finality of death, or the uncertainty about what, if anything, lies beyond, science invites us to open rather than close, to embrace questions and cultivate gratitude for each conscious breath. In living with this uncertainty, we find humility, a gentle recognition that being aware, even for a moment, is its own kind of miracle. So as you breathe deeply and surrender to the hush of sleep, let these questions saturate your dreams, not as worries, but as invitations to live more curiously, more tenderly, and more bravely in the luminous present. As our voyage draws near to rest, let's quietly meditate on a theme that feels at once scientific and human, finding, amid the unanswerable, either a quiet quantum hope or a gentle acceptance. Even as we've traced the limits of science and the boundaries of our current knowledge, there is grace in recognizing both the allure of possibility and the wisdom of letting go. Quantum physics itself encourages awe. It suggests, with mathematical certainty, that every atom within us is part of an unbroken story of the cosmos. We are all made of particles forged in ancient stars, entangled in a cosmic dance whose range defies our intuition. The idea that quantum information is never truly erased, that the universe keeps a ledger, however entangled, offers a sliver of poetic continuity. In this vision, nothing about us is simply lost. Every breath, every heartbeat, every memory becomes subtly woven into the fabric of the world, even as individual form and selfhood dissolve. This, for some, is a source of quantum hope, a sense that being has consequences that echo onward, even if the experience that is you does not persist unchanged. Yet science, as we have seen, sets clear boundaries. The miracle of conscious experience, a first-person vantage woven from living activity, is fleeting, uniquely precious for its impermanence. The hope we find in quantum conservation is not an afterlife as traditionally conceived, nor the survival of identity, but a testament to the interconnectedness and continuity that bind us to stars, time, and all living things. Gentle acceptance arises from this understanding. Rather than longing for a guaranteed survival or clinging to what cannot be demonstrated, we are invited to lean into the present. The story science tells is not of erasure, but of transformation, a continuous, unceasing renewal where each pattern of order, once dissolved, becomes raw material for new forms and new possibilities. In this cycle, death is not an ultimate ending, but a beautiful, necessary return, an exquisite fading of the old so the new may arise. With this comes a kind of peace. To know that your atoms, your energy, and perhaps even some quantum trace of your informational pattern participate forever in reality is, in itself, quietly miraculous. You are inseparable from the processes that sustain the whole. You are part of the universe's memory, its tapestry of change. Science gives you permission to grieve what is lost, but also to rest in what endures. Continuity without clinging, wonder blooming from relinquishment. So as you soften your breath, relaxing into the folds of this dark and gentle night, remember that there is a blessing in simply being. A blessing undiminished by impermanence and illuminated by the subtle hope that nothing, not even the briefest whisper of consciousness, is entirely without meaning or echo in the world. Finally, as the night reaches its quietest, let us softly embrace the ongoing mystery of consciousness, a mystery that threads through every question we have explored, and ultimately, one that science is only beginning to illuminate. Throughout our journey, we have traced the boundaries of life and death, quantum law and subjective experience, possibility and limitation. If there is one abiding lesson, it is that consciousness itself remains one of the deepest, most exhilarating enigmas in nature. We have seen how science unfurls the intricate details of life, from molecules and neurons to brains and minds, while also revealing the fragile beauty of awareness. We have followed the quantum world's shimmering probabilities, discovered the principle of information conservation, and examined both the evidence and the disappointments in efforts to connect consciousness to fundamental physics. The mystery endures, how a universe built from matter and energy can, just for a while, internally witness itself. How atoms, through a whispering tapestry of complexity, become the miracle of being. Quantum survival, provocative though it is, has no clear evidence to support the literal persistence of the self beyond the bodily form. Yet, neither does science offer a complete resolution as to why consciousness emerges at all, or where it ultimately fits within the great order of things. What persists is wonder, the ongoing willingness to ask, to study, and to imagine. Scientists, philosophers, and listeners like you are part of a tradition spanning centuries, a tradition that honors both the rigors of experiment and the necessity of humility in the face of what we do not yet know. Accepting that uncertainty is not defeat, it is an invitation. To rest in the unknown is to be fully present, to marvel at life's possibilities without demanding certainty, and to appreciate both the questions and the fleeting gift of an answer when it comes. Whether consciousness is an emergent miracle or something far stranger, its existence is already wondrous beyond measure. And so, as you sink even deeper into tranquility, gently remember, it is all right not to know. To ask is to honor reality. To sleep is to trust that you yourself are woven into the universe's deepest stories.